Okay, in this video we'll be looking at using vectors to prove geometry things. We'll be giving a couple of examples which hopefully illustrate a few general approaches that may be useful when using vectors to prove things. Okay, generally I like to think of solving these problems in several sort of steps. The first is, I think, by far the most important. Okay, it's to carefully choose your coordinate system. That includes things like where to place your origin. We'll be looking at that a lot in this video. The scale of your vector space, if that applies, and so on. Okay, and it's worth mentioning when solving more a physics style of problem. This skill would extend to, say, choosing which direction you might want to be positive, or whether to maybe even tilt your axes if there's a ramp or something, or whether to even use XY axes at all, or if a sort of radial polar system is maybe more appropriate. Okay, but we digress. The second step after choosing your coordinate system is then to pinpoint all vectors of interest. That is, to be able to write down all vectors that could be useful or make up part of your problem. Okay, this really is connected with the first step because you should be choosing your coordinate system in such a way that this second step now is natural and easy to do. So you're meant to be sort of looking ahead at this step as you choose your coordinate system, and you'll see what I mean when we get there, okay? But you want to make life easy for yourself. The third step is then to actually investigate your problem, which is where most of the so-called work is done. But really, if you've done the first couple of steps carefully, then the problem almost solves itself. You just follow your nose, and so long as you're fluent with all the other vector work you've done, you're quite likely to get what you want. Okay, so most of my general advice will actually be for the first step, okay, how to carefully choose our coordinate system, our origin, where we're going to sort of build all our vectors from, okay. Alright, the first problem we'll look at is to prove that the angle in a semicircle is always a right angle, no matter where you put it on the circumference. So we'll leave it here, say. Try to avoid any artificial symmetry when setting up your problem, okay, so just make the setup as general as possible. We'll also remove the right angle marking, since that's the thing we're trying to prove. So first we need to choose a point to place our origin at. Okay, and there are a couple of points of interest we could maybe pick from. My first tip would be to see if there's any symmetry in the problem that you can leverage. Okay, a circle, obviously, has an extreme amount of symmetry, but all focused around its center. So I think that would be the natural place to put our origin. Something to get used to would be to not really need to draw the axes anymore, otherwise things can get a bit messy. We're really just using this origin as a reference point from which all our vectors will come. So now we should be able to easily write down all vectors which may be of use to us. First, the right end of the semicircle. We call this the vector maybe r, okay, for radius. Note, once again, we're using bold font for vectors. Look, the coordinates of this vector r would actually be something like maybe like a normal r0, where the number r is the actual length of the radius, a number, not a vector. But again, it might be even simpler to not worry about that. Just keep in the back of your mind that this vector r has some sort of radius length that stays the same. Okay. Then the vector going to the left end would be the vector negative r. Again, if we wanted coordinates, it might look like the number negative r and the number 0, but we won't really need that. Okay. Then the vector going to our point on the circumference is quite unknown because he can spin. So we'll just call him v. The only thing we know about v is that his length is equal to the radius of the circle, which we can now write like this. Okay. Okay, so what do we do with these? Well, we're really interested in this angle, aren't we? So naturally, we'd need to also write down the vectors that make this angle. But this vector here is just the vector going sort of from r to v, so we can write it as the difference vector v minus r. Likewise, this vector here is just the vector going from negative r to v, so we can write it as the difference vector v minus negative r, or v plus r. So now that we have these two vectors, how do we investigate the angle between them? Well, we have a dot product for that. In particular, if we're trying to see if they're perpendicular, we'd be hoping that this dot product ends up being 0. So let's see. Okay, we'll take the dot products. We have v plus r dot v minus r. So we know we can use an expansion pattern on that. We would get v dot v plus r dot v minus v dot r minus r dot r. Now, v dot v would just be the length of v square. R dot v is the same as v dot r, so they would just cancel. And r dot r would just be the length of r squared. Okay, so what we have is the length of v squared minus the length of r squared. Okay, but we know that v and r are the same length since it's both the radius of the circle, so that means this must be 0. Okay, and so if those two vectors have a 0 dot product, then they must be perpendicular, so we're done. Okay, so that's the first sort of tip we have for you in setting up your problem. See if you can use symmetry. Okay, it's often quite powerful, and a lot of results can fall out quite quickly when you look at symmetry and you make use of it when setting up your problem. Okay, the other problem we'll look at deals with a triangle. In particular, it's altitudes, which are lines going from one vertex to the opposite edge, making a right angle with that edge. The problem is to prove that these three altitudes are concurrent, that is, that they meet at a single point. Now for this setup, symmetry might not be applicable because there isn't any sort of inherent in an arbitrary triangle. That's sort of the whole point of the problem. We're trying to prove something kind of symmetric-ish about it. We could try placing our origin at maybe one of the vertices. That might be a good place to try. Okay, that would give easy access to the three edges of the triangle because two edges would be connected directly to the origin. Then we could just use a difference vector for the third edge or something. But if we look ahead a little bit, okay, we're interested not in the edges, but in the altitudes. And so say this altitude here would be kind of hard to get a handle on. Okay, you could describe it using vectors. It'd be some sort of difference with some kind of projection, but you can see that would quickly become very messy and yuck when you need to prove that like three of them now meet at a single point. That would be quite disgusting. So what can we do? We absolutely cannot start by assuming the thing we're trying to prove, but we can try and get sort of as close as possible. So here's what we mean by that. We need to prove that these three guys meet at a single point. So right now, that's not an established fact. But what we can take as an established fact is that two of them will meet at some point, since there's no way two altitudes can be parallel if the thing is honestly a triangle. So let's try placing our origin here instead. Okay, and now we'll go ahead and set up the vectors we're interested in, but at the same time, we're going to think through why this setup might be promising. Okay, so do note it's definitely not the only way to approach this problem, but I think it's a nice one, and I hope you'll see why soon. Okay, so the triangle is still an arbitrary one, which means the three vertices would be at three random vectors, A, B, and C, which we absolutely have no control over. Great. Okay. The edges of the triangle will also be of interest to us, but now they'd all just be difference vectors between A, B, and C. I won't go over the details this time, but they are all difference vectors. So here's the first reason this setup is real promising. We've got a pretty clean handle on every vector of interest, I think. Okay, so let's look a bit closer at these altitudes we've got right now. Okay, we've defined the origin to be the point of intersection of these two altitudes. So what this tells us is that vectors B and C aren't just representing two vertices of the triangle, they are also pointing in the exact direction of their two respective altitudes. For example, the vector b here is pointing in a direction which is perpendicular to this edge of the triangle, which is represented by vector a minus c. And so we can write that by saying that b dot a minus c must be 0, because they're perpendicular. Okay, and for fun, we can expand this as a dot b minus b dot c equals 0. Okay, and we can just rearrange that to see that a dot b equals b dot c. Now, likewise, vector c is perpendicular to the edge vector b minus a. So you could do exactly the same thing with that altitude, and you would find that in a similar way, b dot c equals a dot c. And now if we glue these two guys together and sort of cut the middle man, we could conclude that a dot b equals a dot c as well. Very cool. Okay, but here's the real kicker. By setting things up this way, we can actually change the way we think about the problem. Okay, since we've already locked down the point of intersection between two altitudes, we only need to prove that the final one passes through the same point. But this is equivalent to just proving that vector A is perpendicular to this bottom edge here, because if so, then this third and final altitude must pass through our origin, which we have defined to be the point of intersection between the two other altitudes. Okay, so we've boiled down the question to just another perpendicular proof to prove that vector A is perpendicular to the bottom edge, which is just c minus b, then we'd be done. Okay? And that's something we can easily investigate using our dot product again, so let's just do it, okay? We'd be taking the dot product between A and C minus B. Okay, we'd expand to get A dot C minus A dot B. But now that we know A dot B and A dot C are equal, well, the answer must be 0. Okay, and so that means A is indeed perpendicular to C minus B, and the proof is done. Okay, so let's come back to our general sort of structure for solving these problems, okay? What you write on paper is pretty much just the third step here. But I hope you've seen that by far, most of the brain power, almost the entire problem-solving process, comes from carefully thinking about and doing these first two steps together. Okay, so what principles have we seen for doing this well? Well, first was to see if you can use symmetry. That gave us the circle one quite painlessly. Okay, but what was the takeaway, I think, from the triangle one? I think the main idea was to try to simplify the problem. Okay, it might be a bit vague right now, but by choosing the origin the way we did, I think we simplified it in at least two ways. Let's have a look. One was algebraic. We could easily write down vectors representing the positions of the vertices, the edges of the triangle, and even two confirmed altitudes. Okay, and we'd take this over having to deal with like projections and stuff any day. Okay, then this gave us a more important, I think, simplification of the problem, which was that rather than having to prove that 3 line segments all meet at a single point, which is normally quite messy and a lot of equations and stuff, right? It seems kind of hard. We could equivalently just check that a single vector is perpendicular to another vector, which is much easier, and we have tools like the dot product exactly built for that thing, okay? And so I want you to notice as well that the actual step of investigating the problem was only really these 2 last lines here. Okay, that's the only time we actually thought directly about the question. Okay, all the hard work was actually done in setting up the coordinate system and properly noting down all the important vectors and the known information about them, writing them all in sort of vector language, and all this made the actual proof quite easy in the end. Okay? Alright, so I reckon all the skill in solving these problems really comes from these first 2 steps, okay, from setting up your problem well. Okay, so see if there's any way to use symmetry or to otherwise simplify the problem for yourself, and as always, be looking ahead, trying to foresee the next few steps and see what looks most promising. Okay, but that's all we have for you today, so thanks for watching. I'll see you around.